So the role of the data acquisition and the experiment control system is to acquire, monitor and record the data from all 18 detectors and to control the functioning of the whole experiment. In the ALICE detector we will have several million events per second. Only a couple of thousand are interesting for us. And one event is too complex to analyze it on the fly. So the DAC records the event and stores it for later analysis.
We are now in the ALICE control room from where the experiment will be controlled. It's a bit empty today, but in a few months from now we'll have a lot of activity here, night and day. I will show you one of these operation posts. There will be several of them to control HLT, DCS, trigger and DAC. If we want to start data taking now, the only thing we have to do is click on this button of the experiment control system to start a run. It will start the different processes on all the machines, control that everything is going on, and from this window down, which is the data acquisition run control, we see the status. Now data is flowing in the different computers and is being recorded. In this area we have all the logs of what's going on, so as soon as something happens, if we stop the run, we see the different messages coming in. The processes are being stopped now, and the run is finished with success. There has been no error.
The detector data link consists of three components. On the detector side, the source interface unit will convert the electrical signals coming from the detector components to a multi-gigabit optical stream. The optical signal will travel along a multimode optical cable, which can be up to 200 meters long. Unlike here in the lab, in the final system it's impractical to use one long cable. Instead, the cables will be segmented and special patch panels will be used to connect the cables to each other. On the receiving end, in the PC, we will use the readout receiver card. The readout receiver card will convert the optical signal coming from the link, convert it back to electrical signal, and store it in the local memory of the PC. By using a standard interface, the PCIX interface, we are allowed to use standard commodity PCs. They are like any other desktop PCs, but a bit more powerful.
As Csaba has explained to you, here we have one of the patch panels with all the links we have to the front-end electronics, and through which the data acquisition reads the data from the electronics, using the DROC cards Csaba has shown you.
This is an example how the detector data link is going to be used in ALICE. This is the readout control unit of the biggest ALICE detector, the time projection chamber, the TPC. As you can see here, the source interface unit connected to the RCU, and the optical signal travels along the optical cable, and finally it arrives to the PC where the readout receiver card, the DORC, is sitting.
This is our DAC reference system, and you can see here these two racks. So this rack is the same as in point 2, and we have here a few LDC machines and which are taking the data. The data itself is coming from this bunch of machines, the so-called DDG machines. So they are generating the same data as the detector would be. So they go by these fiber channels in, will be processed, and then go to these two machines which do the event building.
This is the event building network, which has two functions. First of all, it is used to connect all the machines here in the room so they can exchange data. And the second function is to connect all the machines or the data movers to the computing center so that it can write the data to tapes. So here you have the core of the data acquisition system. Again, on top, PCs that assemble the individual fragments of an event into one complete picture of what happened in the detector. And through a storage network, they are connected to about 500 normal hard disks that store the data before it is being moved to the computing center for long-term archival. And right now, at the moment, the whole system is used for the Data Challenge 7.
Much higher. See, this is from since Monday morning. The free memory is about 1 gig. Before it was almost down to 0. So probably the stream recorders, each instance is taken.
Part of the data acquisition system are also machines for data quality monitoring and experiment control.
I'm going to show you the implementation of the T0 module for Mood. We're going to use a file taken by T0 test team in October. Now we are going to take a statistics of 10,000 events from this file. There are various electronic channels. Here there are two-dimensional histograms.
And could you take a profile out of it and make a fit?
Yes. So this is standard root facilities. So
the problem we have discussed a long time with the trigger people and with the pixel people is the handling of the PIT, where PIT means pixel trigger system. Now, after many discussions, we agreed that the handling of this item requires the introduction in the interface between the ECS and the trigger of a new object that we will call the TIN SPD. It will be a process performing the role of SMI proxy. It will have a certain number of states, and it will be watched by the ECS component.
Okay. And how will you put the object into toggling mode or signature mode?
Now, the CTP will see this object as a DIM server, and it will send the commands, DIM commands to it, ignoring the status from the SMI point of view.
So here we have the database for the machines and racks in CR1. We have different machine types. I can give an example for the GDC, where we have this machine. And then if we click here, we can see the details, the general information, the network information and power information. Here, for example, we have the IP address and then the network service that this IP corresponds.
So now if you click on the rack, you go back to the list of machines for this rack?
Yes, that's true. So you have the machines on this rack. And then if you click again, you can have the details of it, any machine.